Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to be talking some more about chemical kinetics. So, in the last video, we did some revision on slopes of graphs, okay? And we talked very, very briefly about how slopes of graphs are important when it comes to a study of chemical kinetics. Today, we are going to look very much more in depth at that. And we are going to see how we're going to define what the rate of a chemical reaction is. In other words, how fast a particular chemical reaction occurs. Okay, so let's start off by looking at a good old generic chemical reaction. A moles of A is going to react to give us B moles of B. Okay, so how are we going to define the rate of this particular reaction? Okay, so again, rate is all to do with how fast or how slow, I guess, a chemical reaction occurs. So, you know, what are we going to do? Are we going to say, right, we're going to talk about how fast this reaction goes in terms of all of the A disappearing? So in other words, the time that it takes for all of A to disappear? Are we going to talk about it maybe in terms of how fast B appears in the reaction? In other words, how quickly or what sort of length of time it takes for all of B to be formed? Well, the answer is kind of a bit of both, really, to be frank. And so what we're going to do is we're going to start by considering the fact that in any particular chemical reaction, what is happening is that the reactants are decreasing in concentration over time and the products are increasing in concentration over time. Okay, so when we're talking about rate, this whole thing about time becomes very, very important. And when we're talking about rates of chemical reactions, what we really want to know is what is the concentration of A at a particular time in the reaction and what is the concentration of B at a particular time in the reaction. Okay? So in other words, and this is where the whole calculus thing became important last time, how is the concentration of A changing over time? And how is the concentration of B changing over time? And when we're talking about change in anything versus time, that's a rate. Okay. So, if we were to, let's say, plot the concentration of A and B over time, so this axis here, our y-axis is concentration, our x-axis is time, what we might get is something that looks like this. The concentration of A will be decreasing, of course, and it might decrease in a manner like that. The concentration of B starts at 0 and it's going to increase, and its concentration might look like that. Its concentration versus time curve might look like that. Okay, so what we're talking about now is the rate of change of concentration of these guys. The rate at which the concentration of A is decreasing over time, the rate at which the concentration of B is increasing over time. Okay, so when we're talking about rates, as I said last time, we are interested in slopes. In other words, the rate of change of concentration of A at any time is related to the slope of this graph here in blue. And the rate of change of concentration of B at any time is related to the slope of that curve of B versus time. Okay. So let's then get into what looks like maths, okay? And we're going to say, okay, we are going to now define what we mean by the rate of the reaction. We are going to say that the rate of this reaction is going to be equal to the rate of change of concentration of A with time. And it's also going to be equal to the rate of change of concentration of B with time. That's how we define our rate, okay? You might say, where do those equations come from? They don't come from anywhere. These are the formal definitions of what we mean by the rate of a reaction. Now, there's a couple of problems with the way that we have defined this that we have to fix. Okay, first up, from those plots of those graphs of A versus time and B versus time, you will notice that the concentration of A versus time, the slope of that graph, is always negative. And the concentration of B versus time, that green curve, the slope of that curve is always positive. So what we are going to need then is to take into account that fact. So rate is going to be equal to, we're going to need a negative sign in front of our rate of change of A versus time. Because the slope of that graph is always negative, we're going to put a negative out of the front so that we get a positive rate. You can't have a negative rate. It doesn't make any sense. Okay? So we take our negative sign there and we're going to put that there. And now, have we solved all the problems? Not quite. Not quite, because we also have to take account of the stoichiometry of the equation. Okay? Let's do a little thought experiment. Let's replace these A's and B's. Let's replace them by actual numbers. Okay? So let's say 1A gives 2B, let's say. Okay? And let's think about how the concentrations of those now are related. The change in concentrations of those are related. Every mole of A that reacts gives 2 moles of B. Now, think about this. What does that mean? That means that the concentration of B is changing twice as fast as the concentration of A. Okay? Because for every mole of A, you are getting 2 moles of B. Okay? Every mole of A that reacts gives you 2 moles of B. So if the concentration of A is decreasing at a particular rate, then the concentration of B has got to be, yep, you guessed it, increasing at twice that rate. Okay? So therefore, the way that we take account of that when we define our rate is we are going to say that the rate of the reaction is minus 1 over little a multiplied by the slope of that graph, dA by dt. And that is also equal to 1 over little b multiplied by the concentration change dB by dt, okay? And now we're all good. Now we're all good. We have now a definition of rate that will give you, most importantly, the same answer depending on whether you are monitoring how A decreases over time or how B increases over time. Okay? We've taken account of the fact that the concentration of A is always decreasing, so we're putting a negative sign there, and we're taking account of the fact that the stoichiometry will determine the rate of change of the reactants and the products. Okay? And so putting the little factors here, the 1 over A and the 1 over B, ensures that the answer we get for a rate is going to be independent of the stoichiometry of the reaction. And that is precisely what we require. Okay. Now, so there you go. That's how we define the rate of our reaction. And you're probably looking at that, some of you anyway, and thinking, oh, this is calculus, I can't do it. You can. You absolutely can. And remember, this is just terminology. This is just shorthand for the slope of a graph. That's all that it is. And you all know about slopes of graphs. Okay, you absolutely all do. So having then shown how to define the rate of a reaction, the question then becomes, right, how the heck do we measure the rate of a reaction. Okay? Because as we've said, as is obvious here, the rate of the reaction is dependent on or related to the rate of change of the reactants and the products. But, as we said before, they are always changing, aren't they? Go back to our little picture of concentration of A versus time. Okay, it's a curve. We'll see why it's a curve a little bit later on. Here's your concentration of A. Here's time. The rate of the reaction is changing at every point. So what the heck? Okay, every time you measure the rate of the reaction, it is going to change, isn't it? So that makes measuring the rate of the reaction, if you think about it, that makes measuring the rate of the reaction really, really difficult because it's changing at every point in time. As soon as you've measured it, it's changed. So how do we get around that? Well, the way that we do that, we cheat a little bit. We cheat a little bit. And what we're going to do is we're going to look at this area here. We are going to look right at the start of a chemical reaction. We're going to look right at the start of the concentration versus time curve here. And if we were to blow up that section, which we're going to do here, we're going to blow up that section, and what we would see is, in fact, that if we blow it up, ooh, it looks pretty much like that, doesn't it? It looks pretty much like that. In other words, right at the start of the reaction, the curve is nearly linear. Okay? And that's going to make life a lot easier for us, because if the curve is nearly linear, then the slope of that curve really at the start of the reaction is not changing very much. And so therefore, that makes it easier for us to measure the rate of the reaction, because all that we need to do is to go to the very start of the reaction and measure how the concentration of A, in this case, decreases over a short period of time. We have to keep that period of time short, because if we make it too big, then the curve is no longer linear, or essentially linear. Okay? And this is called the method of initial rates. And this is what you will often find when people do kinetics, is that they look only at the very, very start of the reaction, and they can determine what the rate of the reaction is from the very, very start, because the rate of the reaction at the start is essentially constant, because that curve is essentially linear. Okay? And then, as I said, all that we need to do, once we've done that, we monitor the concentration of A over a short period of time. You essentially draw that graph, you measure its slope, voila, you have got yourself the rate of the reaction at the start of the reaction. Okay? So, I think we might call it a day there, because I was going to tell you more, but that'll have to wait for the next video. And so in the next video, we're then going to talk about rate laws. And we're going to do some practical stuff. We're going to look at some numbers and rates of reactions and figure out all about chemical kinetics, okay? So, in that case, we will see you in the next video.